Welcome to this explainer. Today, we're unpacking a genuinely fascinating piece of source material that reveals the systematic genius behind semiconductor engineering. If you've ever looked at a computer chip and wondered how on earth human beings actually manage to create something so infinitesimally small and impossibly precise, well, you are in the right place. So let's jump right in. Have you ever wondered how the microscopic, hyper-complex world of microchips actually gets built without just failing constantly? I mean, think about it. A single stray atom, a microscopic fluctuation in temperature, or the tiniest vibration can completely ruin a modern microchip. So how do engineers consistently solve these seemingly impossible physics problems to keep our whole modern world running? Well, the secret isn't just sitting around waiting for some random lightning bolt eureka moment from an isolated genius. It's actually a highly systematic, repeatable process driven by exactly 40 foundational problem-solving principles. Yeah, exactly 40. It is a highly structured discipline. And that brings us to the visual guide we're looking at today, Dr. JP's essay TRIZ40 Framework. It's essentially the master grid of semiconductor problem solving. You can think of it kind of like the periodic table, but instead of chemical elements, it's a table of engineering problem-solving strategies perfectly adapted for the semiconductor industry. Now, this chart is completely packed with dense methodology. So to make it easy to digest, we've organized this explainer into 6 quick parts. 1. The Innovation Challenge. 2. The TRIZ40 Framework. 3. Rethinking processes. 4. Mastering materials. 5. Preventing errors. And finally, 6. Engineering creativity.
All right, kicking things off with Section 1, the Innovation Challenge, where we're dealing with incredibly high stakes and tiny margins.
To tackle those massive stakes, we first need to understand what TRIZ40 actually is. Now, TRIZ is a Russian acronym for the Theory of Inventive Problem Solving. What Dr. JP has done here is create a highly specialized visual adaptation of that methodology specifically designed for the unforgiving hurdles of making microchips. It translates abstract innovation theory into the strict reality of process innovation, yield thinking, and hands-on engineering education.
Moving on to Section 2, the TRIZ40 Framework. This is where physics literally meets the factory.
A fantastic example of this framework in action is how engineers handle hyper-delicate components. If we compare standard physical contact operations with Principle 28 from the guide, which is mechanics substitution, we see a total mindset shift. Instead of risking a physical touch that could easily scratch or contaminate a wafer, the principle prompts you to substitute that action with optical, electrical, or chemical methods. Boom, you've completely eliminated the risk of physical damage. That leads us right into Section 3, rethinking processes, or basically flipping manufacturing on its head. What's super interesting here is Principle 13. It's simply called the other way round. It literally tells engineers to look at a problem backwards. When your standard process flow hits a brick wall and progress stops, the framework explicitly demands that you pause and ask, hey, what if we just do the exact opposite of what we normally do? And as the source details, that kind of inverted thinking has massive practical applications. Principle 13 can drastically improve your final yield of usable chips. Or take Principle 22, appropriately named Blessing in Disguise. This one pushes engineers to turn a negative into a positive. For example, taking the immense, usually destructive waste heat generated during manufacturing and systematically capturing it to power another part of the process. You're literally turning a liability into an asset. But what happens if a certain manufacturing stage is just too risky, highly prone to defects? Well, Principle 21 outlines a brilliant 2-step approach for that. Step 1, locate those highly sensitive defect-prone stages. And Step 2, figure out a way to quickly pass through them, or better yet, skip them altogether. It teaches you that sometimes the most elegant way to solve a problem is just to design a process that sidesteps the danger entirely. Next up is Section 4, Mastering Materials, which is all about overcoming hard physical limits. The TRIZ40 framework gives us specific material solutions to get past those physical limits. Principle 17, that tells us to move from standard 2D designs to 3D stacking, basically building microscopic skyscrapers when you run out of flat real estate. Principle 14 suggests using curves and fillets to keep brittle materials from shattering under stress. And it doesn't stop there. You've got Principle 31, advocating for porous materials for advanced filtration, and Principle 40, using composite materials to seriously beef up chip packaging. It's basically a masterclass in manipulating physical reality to serve the microchip. All right, rolling into section 5, preventing errors, or how to fix future defects. This really begs a crucial question. In a world where one invisible speck of dust can ruin $1 million batch of silicon wafers, how do you fix a microscopic defect before it even occurs? Seriously, how do you solve a problem in the future? The visual guide answers this beautifully with Principle 10, Preliminary Action. It outlines clear preventative steps. Step 1, identify your highly sensitive surfaces well before the main process even begins. Step 2, pre-activate or pre-treat them. You essentially prep the battlefield ahead of time so the defect doesn't even stand a chance. And it builds on this defensive mindset with a whole suite of preventative principles. Principle 9 demands pre-compensation to stop later defects. Principle 11 advises adding protective layers, acting as beforehand cushioning before handling damage can even happen. And Principle 25 goes a brilliant step further, telling you to design equipment that self-cleans and self-calibrates, completely removing the error-prone human element from the equation. Which brings us to our final part, Section 6, Engineering Creativity, proving that it's a teachable discipline. When you look back at the entire SAIT Zeros 40 grid, it becomes crystal clear that this isn't just a haphazard list of neat engineering tricks. It is a unified visual language for problem solving. It stands as absolute proof that top-tier engineering innovation isn't an accident. It's a rigorous, teachable discipline. As the source document explicitly states right in the footer, the core mission here is to act as a foundation for semiconductor creativity, process innovation, packaging, yield thinking, and engineering education. It's built to train the minds of the next generation of engineers to think systematically, not randomly. Which leaves us with one final provocative thought for today. If the most complex, precise, and technologically demanding industry on the planet relies on a highly structured framework like TRIZ40 to overcome its obstacles, what systematic tools are you using to solve the impossible problems in your own world?